All right, let's see. So I have 2 hours, correct?
Yes.
And please, it's a small group. Interrupt me if you have questions or hold them, and I'll make sure we have time to get to them. But I was asked to talk about ICD basics, and I've seen the titles of the course of the lectures you've had up to now and work you've done up to now, but not the details. By the way, is my audio okay?
Yeah, perfect. Was.
Okay, good. Okay, so we're going to talk about generator technology, sensing cardiac electrical signals, arrhythmia detection and discrimination, defibrillation lead components and lead failure, and defibrillation shock waveforms. So starting with technology in the generator, we're going to cover batteries, charging circuits, storage capacitors, how arrhythmias are sensed and detected, and what happens when you put a magnet on a pacemaker or defibrillator. So if we think about what goes inside an ICD generator, if we think about the three main aspects that take up volume in the generator, inside the can, there's the electronic circuits, which is about a third of the volume. There's the battery, which stores electricity at low voltage, which stores energy at low voltage, and the capacitors, which the high voltage capacitors store electricity at high voltage. So I have a question. Why don't we just store the energy in the shock capacitor, put it in at high voltage in the factory, and that way we could make a smaller defibrillator because everybody wants a smaller defibrillator. So since nobody's going to volunteer an answer, does anybody know the answer to this question? Do I have to call on you individually?
I don't know the answer. So
well, no, that's a good question. Okay, so now you're at the right lecture. It just shows this is the right lecture. That's good, right? So why is that? Okay, no, and why do I ask questions like this? That's a good. Hold on, my slides are not advancing. Okay, hold on for a sec here. Well, I asked it because to quote America's first ambassador to France, Benjamin Franklin, he had this many aphorisms, and he said, "Tell me and I forget, teach me I remember, but involve me and I actually learn." So it doesn't matter if you know the answer. Just thinking about it is a good thing, right? Okay, so now you're interested. The answer is energy density. The energy density of energy in a battery stored as chemical energy is about 1,000 times the energy density of energy in a shock capacitor. So the reason we don't do that is you'd only have enough energy to deliver one shock, and you couldn't run any of the low voltage components in the device that keep it operating and keep it thinking to, and the key point is that storing electricity at high voltage is much less inefficient than storing chemical energy at low voltage. So what else goes into a defibrillator when we look at it? Well, it's important to separate the header where you connect the leads from the electronics package, and what separates them are these feed-through circuits. Why do I point them out? Because outside of the device, the header is in the electromagnetically noisy environment that we all live in. But inside the device is electrically isolated from the rest of the world, so that the only signals that get in, ideally, are the ones coming through the leads, and that these should only be carrying cardiac information. And a lot of work is done, you'll see, to keep the electrical components electrically isolated. When you have an electrical component that radiates, like the long-range radio frequency transmitter that we use to communicate with devices over, or the Bluetooth one in some devices, you have to shield that. That's why there's a plate over it. Defibrillators and pacemakers also have a short-range antenna that we use when we put the programming head of the programmer over the device. There is a high voltage transformer that we'll discuss later that converts low energy electricity to high energy electricity. And that we're going to come to, I mean, low voltage, excuse me, electricity to high voltage electricity. We'll come to that later. Okay, so what about batteries? Honestly, I hated battery technology when I studied it, but I want to break down the things that are clinically relevant about battery design and battery components. So all batteries use lithium as the anode. The battery capacity of an implantable defibrillator is somewhere between 1 and 2 ampere hours, depending on the model and the company. To give you an idea, the new iPhone 13 has a 3 ampere hour battery, and you recharge that every night. So the point is, we really need energy efficient circuits in a defibrillator to keep it running for 10 years and still have half the energy left over to deliver shocks. When we think about a battery, we think about its, in addition to its capacity, the energy density. This tells us how efficient it is at low power for pacing and how big a battery you need. The other thing we care about is how quickly you can pull electricity out of it. There's some batteries that are super efficient for storing chemical energy, but you can't get energy out of them rapidly. And if it takes you 5 minutes to deliver your shock, the patient's going to be dead. And finally, we'll come to this, what's called a discharge voltage curve. We'll see that the way the voltage change as the battery depletes in energy can be used to indicate when the battery is running down as a replacement. Finally, I don't want to get into the weeds on battery design, but the basic concept of all batteries is that there are layers upon layers of lithium metal separated by a separator and then surrounded by some cathode. The goal is to make this separator as thin as possible, because all it does is keep the lithium and the cathode from reacting and shorting the battery, turning into heat, draining the battery immediately. On the other hand, if the physical properties of the cathode change as chemical reactions occur, crystals form, it puts a little force on the separator. If you puncture that separator, the battery's dead. So battery design is a complicated art. And when you hear somebody has a battery problem and some of the batteries fail unpredictably, it's often, although not always, a problem with separator perforation or some other area in which the lithium and the cathode make direct electrical contact as matter is deposited on the cathode during the course of the battery depletion.
Check.
Okay. Yes.
This is the problem, the current problem that the SICD batteries have, or you know, the sudden drain of battery, the recall. This is something.
Yeah,
like
no, I apologize. I did. No, that's a really good question. I have to look that one up. I don't remember the reason in SICD.
Okay.
The other, so there are a couple of possibilities. One is the battery itself. And the other possibility is always there's some other electrical component the battery is attached to, right, that shorts and is pulling continuous current out of it. And I apologize, but I don't recall what the failure mode was in SICD.
Because there's the same recall on some biotronic ICDs and also some Abbott pacemakers. So
right. So I do know the Abbott pacemaker one. The Abbott pacemaker one was that lithium crystal, as the battery deteriorate, as the battery depleted, lithium crystals formed on the anode electrode, and those crystals increased the size of the electrode, and it ruptured the separator and went and touched the, connected directly to the cathode. And that's what happened in that battery. There were older Medtronic and Biotronic batteries that had separator perforation problems. It's been a year or two since I looked at the SICD problem. Okay. I don't recall that, but yes, this is what happens in the Abbott pacemakers and in older Medtronic and Biotronic battery problems.
Okay, thank you.
No, my pleasure. See, that's how you guys should interrupt me. Okay, battery discharge curves. Well, discharge curves can be useful because they tell us how long we have until the battery runs out. So I want to give you these terms that you may hear and you might have heard in previous lectures, but just to remember them when you're taking care of patients. The recommended replacement time is an indicator that comes up, and that should tell you in a pacemaker that you have 6 months, and in a defibrillator you have 3 months until the device is no longer guaranteed to work. And now it turns out not every company gives you 6 months, but the mandate is to give 6 months. In the period between the recommended replacement time and end of service, that when they don't guarantee the system, this is called a prolonged service period. Why does anyone care? You don't care about the name, but you do care about the fact that the actual function of the device, not mission critical functions, but some functions may be altered in this period. For example, you may have less electrogram storage in a defibrillator. Pacemakers might not have a rate responsive mode. One company goes to dual chamber devices, go to single chamber, and various other features might not be available. And so it's important to know, because if you want that feature and it is not turning on, you really want to see if the device is close to end of service. So what is a battery discharge curve? A battery discharge curve tells you how the voltage of the battery changes over time. This is a battery discharge curve of carbon monofluoride. It's a very high energy density battery, but you can't really pull energy rapidly from it. This is the energy discharge curve of a silver vanadium oxide cathode. Silver vanadium oxide has 2 different voltage plateaus, and these can be used as this one and this one as end of service indicators. And the reason it does is that vanadium has 2 different valence states, +2 and +4. If you combine silver vanadium oxide and carbon monofluoride, you get a discharge curve like this. And so when the voltage goes down to this level, you have an indicator. And for example, if you look at the pacemaker programming screen, as Sylvain and Pierre do every day, you see battery voltage 2.94 volts, recommended replacement time voltage 2.73 volts, and they give you an estimate of how long you have. On the other hand, there's another company that uses a different cathode technology, manganese dioxide, which is has the advantage that it both will allow you to pull high power and has pretty good energy density. But you can see there is a constant voltage pretty much until the curve goes, the battery is completely out. So in these types of batteries, you'll never see a voltage given. And in fact, what the manufacturers do is build in what they call a charge meter. They measure the current coming out of the battery and they integrate it over time. And so what you see is this little kind of fuel gauge to tell you, how much charge has been taken out of the battery, so they can do the bookkeeping to know when to replace it. Doesn't really matter how you do it, but the battery chemistry dictates what your end of service indicator can be. Now, what determines how long a pacemaker? Oh, yes, please.
We have a question.
From the previous graphs, is it possible to deduct the energy density and the maximum discharge rate based on those graphs purely?
No, this is only voltage.
Okay.
Right? This is only the voltage. It does not, and this is, as you see, just percent. You cannot tell those.
Yeah.
And Chuck, I have another question, if I can.
Please.
Because it's true that we don't see this technology. We don't learn a lot about batteries, also in daily practice.
I know.
When I do device checks, I'm always surprised that there's so much variation in Medtronic devices in prognosis of battery life. And sometimes as you can see here also in your example, it can be like 1 + 1 or 2 years, and it can be quite difficult to know when to evaluate the patient. Is that also due to the way that it's calculated, or is it just more variation in this brand than in the other manufacturers?
Right. So the estimate so there are two reasons for this, and these are good questions. This is a little more technical than I was going to get for your students, but since you asked, Mark, that's good. We have there are two reasons for this. In defibrillators, there is an estimated power drain based on the current level of pacing. So let's say, for example, pacing is typical, a dual chamber defibrillator might be 20% in the atrium and 1% in the ventricle, and some nominal amount of shocks. But let's say you increase the patient's beta blockers and they're pacing 100% in the atrium, and the patient gets more shocks, then you're going to then you're going to use more power from the battery. Another thing you could do, and it's a particular problem for Medtronic devices, if you turn on the type of electrogram recording they call pre-storage, which allows you for longer recordings, that's also a significant drain. So this is an estimate, and then for minimum would be no pacing, no shocks, just housekeeping currents. So they give you an honest range, right? Nobody can tell you, but the estimate, that's for their defibrillators. Now their older Medtronic pacemakers don't use the CFX batteries. They use, I forget what they use, and they have a different problem in measuring battery estimates. They give you, typically they'll come up with an estimate that says, 8 months, they'll give you the things that make me crazy. They'll say estimated time to replacement, 6 months, but range is 1 to 14 months, something like that.
Exactly, that's the
reason for
challenge.
that is they use a different end of service indicator. At the end of a battery discharge, the internal resistance of the battery goes up. And you have seen, you probably look at that, and we don't pay a lot of attention to it, but like when a new battery, brand new out of the box, if you look at it, it says internal resistance 100 ohms. And toward end of service, it might be 5,000 ohms. Well, those companies use the battery internal, Medtronic older pacemakers use battery internal resistance as an end of service indicator. So, and internal resistance is notoriously variable, right? The rate at which it increases over time is very hard, has wide error bars, and that's the problem with that indicator. Now you've exhausted almost everything I know about this subject. Okay.
That's perfect, thank you.
I told you battery chemistry was not my strongest field, and for sure it's not. Okay, boy, that looks funny. Okay, determinants of longevity. Well, the most important determinant of longevity is how big the usable battery is in the device. And we can see that, there are older papers on this, but just to let you know that hasn't changed, because in my experience, you talk to the manufacturer, their batteries don't last very long. And then they say, oh, that was last year's device, but this year's device is better, right? This year's, so for those of us who are Jews, we always say next year in Jerusalem, it's like, this year's device is going to be better. The battery's going to last longer. And how do you know? Because it's brand new and out of the box. You can never argue with it. Well, first of all, if you pace a lot, what matters is battery capacity. This has been true for the last 7 or 8 years. The green ones are the companies, oh, I'm sorry, it doesn't, yes, is the company with the largest battery, almost 2 amp hours. The blue one is the company with the smallest battery capacity. And guess what? Longevity, if you pace a lot, and that's a cardiac resynchronization device, pacing 3 chambers, or, at least 2 chambers all the time, depends on battery capacity. If you do almost no pacing, then other things come into effect, because what's consuming your power is the background operation of the system, and then it gets into your circuit efficiency. And the way you get, and longevity then is proportional, if you don't do a lot of pacing, to, well, it's always proportional to the inverse of your power consumption. So that means low background power, of course, efficient pacing and efficient shock charging circuits. And then, of course, turning off features that you don't need, right? If, the patient doesn't need rate response in a pacemaker, you can turn off the rate response, right? I do want to recommend a brilliant paper that is hard reading, and the appendix, which has most of the math, is even harder reading, by a brilliant electrophysiologist in Belfast. If you really want to understand, know more about longevity, Longevity Decoded: Insights from Power Consumption Analysis into Device Construction and Its Implications. Ernest Lau figured out how to hack based on published data, the actual power consumptions of each company's devices, and showed you how to actually calculate how long they're going to last if you increase your pacing outputs or do various maneuvers. And it's simply amazing that he could do this, and he just did a brilliant job of it. This is not something you need to practice every day, but if you're interested in what really smart people can do, I would recommend this paper. Okay. Now, moving on to the question of charging circuits. A key thing about, just a few points about this, all the electricity, right, when electricity comes out of a battery, right, this is direct current electricity, and capacitors are direct current devices, but there's no direct current device that can increase the voltage, right, from 3 volts to 800 volts. And so in the middle of your defibrillator is a little block of ceramic with an iron core that is a alternating current transformer. And these are like the transformers that, for example, heat up in your laptop, right? That little block that when you connect your laptop to the wall, that's the reverse type of transformer. The current comes out of the wall in Europe at 220 volts. Your laptop operates at 9 volts or 6 volts. And so you want to step down the voltage. And of course, there are inefficiencies there, and that's why your transformer can get hot. And the two things to know about this are the power that comes out of a device while it's charging is really quite high. If you do the math, to store 40 joules in 10 seconds at 80% efficiency, which is about what the best modern circuits can do, that is a current of 2 amperes, which is a pretty solid current. And one of the things that's happened in the last 5-10 years is improvements in transformer circuitry efficiency have both shortened the charge times and improved the efficiency. Now, we don't see this much, except you're waiting around while the device is charging, but every now and then you see an indicator on your electrograms that the device is charging. And the reason for that is that even though the charging circuit is isolated from the sensing circuits, that when you turn on a high voltage charging circuit, it radiates electromagnetic energy. Remember, alternating current is the way you made radio waves at the end of the 19th century. And you can see signals come out. For example, this is a patient, and here's a tachycardia, probably sinus tachycardia for the experts on the other side of the Atlantic, but where the defibrillator starts to charge. And you can see as soon as it starts to charge, there's this little funny signal that most of us ignore, but that's the signal from the charging circuit. Now, as the circuit is charging, the energy needs to go somewhere and it goes into the storage capacitors. You probably remember from high school or college that a capacitor stores electricity by separating two electric conducting plates or conductor plates from an insulator called a dielectric between them. And the capacitance is defined as how much charge you store for a given amount of voltage. Now, it turns out the key thing to know about a capacitor is the amount of charge you can store depends on the surface area of this electrode. So a bigger plate will store more electricity. The energy is the product of the charge and the voltage. The voltage a capacitor will hold depends on two things: the intrinsic dielectric strength of whatever the dielectric is. Some dielectrics will hold up, will allow you to have a higher voltage before they break down and become conductors, and others won't allow quite as high a voltage. And then, of course, how thick it is. The thicker you make it, the more, the higher the voltage can be. Of course, inside a defibrillator, we want to keep this thin, and we don't want giant plates. So how do they increase the surface area? Well, the original capacitors used, and they have some important advantages for high voltage capacitors, were aluminum capacitors. And aluminum capacitors came from the photo flash industry. When you take a flash photo, that's energy stored in an aluminum capacitor that's released as light. Now, to make one of these, to make it a lot of surface area, to make it thin, you start with the same foil, you wrap your cooking in, and then you etch it to make like little microscopic crevices, as you see in the scanning electron micrograph. And then modern capacitors also go another step further. They do something called sintering, which is they take little pellets of aluminum and they deposit them. The whole idea is to get as much surface area there. And then the dielectric, the insulator, is an aluminum oxide, which is really nasty stuff, but it's a pretty good dielectric. The other type of capacitor used in Medtronic and Boston Scientific devices, which is a lot heavier, is tantalum. Tantalum is a heavy metal, but tantalum metal can be dispersed as a powder, and the dielectric is its oxide, tantalum oxide. And the main advantage of tantalum capacitors, they have some disadvantages. The main advantage is the dielectric strength is 3 times that of the dielectric and aluminum capacitors. So for the same volume, you can store more voltage in that direction. Now, in addition to storing energy and charge, in addition to storing charge, what does a shock capacitor do? Well, it obviously stores energy, and the key point is energy, right, depends on the square of the voltage. So in electrical shocks, if you double your voltage, you square the delivered energy. And we will see that voltage is really the key thing when it comes to defibrillation. And voltage to defibrillation is like altitude is to a pilot. Now, another important function of capacitors we'll come to at the end is what we call is that the capacitors allow you to determine over what period of time your shock is discharged. This is a function called the system time constant. We use the term tau, the Greek word tau, for a time constant. And the time constant is a measure of how fast the electricity comes out of the capacitor. The voltage goes down to by about 2/3, actually exactly 63%, or to 37%, or 1/e, the base of natural logarithms, the starting voltage. And that time for discharge depends on 2 things. It depends on the capacitance. Large capacitors will discharge more slowly. Small capacitors discharge more rapidly. and the electrical resistance in the shock pathway that you're delivering through, and we'll come to that later. Okay, enough on capacitors. I want to turn now to the process of sensing. So Pierre and Mark and Sylvain and I have spent a lot of time thinking about sensing. And you may have heard a little about sensing in your pacemaker lecture. I'm pretty sure you did. But just to review a few things, sensing is the process defibrillators use to determine the timing of each cardiac electrical signal. And the way we do that is when the signal exceeds a certain threshold, that's the time that is marked. Now here we see some electrical signals not marked here and during this ventricular fibrillation rhythm. And these are not tall enough or don't have high enough amplitude to meet the sensing threshold. Instead of using a fixed sensing threshold, as older pacemakers did, all pacemakers use some version of a dynamic sensing threshold where the device becomes more sensitive, the threshold becomes lower if it doesn't sense any signal. And then once it senses signal, the sensing threshold increases. And the secret sauce behind this varies from company to company. But the goal, when this works right, is not to sense T waves, sense R waves, but if ventricular fibrillation signals can often be very low amplitude, that to make sure we don't miss any of those. And that more correctly, make sure we miss very few of those. Here, for example, only one of them is missed. Now, to use the terms we use, if we have the sensing signal, a sensing threshold that is set, so you sense the R wave, but say don't sense other signals, the T wave, then we call that appropriate sensing. We sense electrical activation, not repolarization or anything else. If we set the sensing threshold too high, we don't sense anything. We call that undersensing. And if we set the sensing threshold too low, we'll sense the R wave, but we'll also sense the T wave, and we'll sense potentially low amplitude other non-cardiac signals, and we call this oversensing. Now, when we look at intracardiac recordings, I want to introduce those of you who are students to the concept of a marker channel. The marker channel is an output from the device, defibrillator or pacemaker, indicating that it has identified a sensed electrogram, and also something about how it classifies it with some letters and often the intervals between the electrograms. But if we just focus on the marker, in an appropriate sensing of a tachycardia, there should be one marker for every ventricular depolarization. If we have oversensing, then that is indicated by the fact that in addition to a marker for the true electrogram, there is a second marker. There's more markers than electrograms. In this case, there's one extra marker for each cardiac cycle because the device is oversensing these T waves. If we look at the marker channel, undersensing is identified by fewer markers than true electrograms. Here's an episode of ventricular fibrillation, which is not being sensed reliably because we now see more electrograms than markers. So from an operational perspective, if you want to know if sensing is appropriate, if there's oversensing or undersensing, you should focus on the marker channel. So here's an example of a pacemaker with a fixed sensing threshold of 2 millivolts. And so we'll ask, do I have to call on the students, or who's going to volunteer? Is sensing appropriate or not? And I'll tell you, this is an episode of ventricular fibrillation.
It looks appropriate.
So, okay. So so let's look at what we have here. We have the mark, thank you. By the way, who said that? What's your name? I didn't, you guys don't have your cameras on, which our students don't either, which is, which is just fine. That way you can be, Facebooking and sipping your cappuccino and all those important things, because it's necessary to do that during lectures that are boring. But who said it was appropriate?
I'm Daniel.
Daniel, okay. So Daniel, let's work on this a minute. This is the signal, right?
Yeah.
There are lots of electrograms, right?
Yeah.
But there are very few sense markers. Are there more signals than markers? Or are there the same number of signals? So appropriate sensing means same number of signals and markers. You think they're the same number? You think there are more markers and more signals than markers?
No, there's more signals than markers.
Right. So what do we call that?
That's
We'll go back.
Under
We'll go back one screen. Right. No, this is why we ask questions. If there are more signals than markers, what do we call that?
undersensing.
Yeah, good. So this
But-
is undersensing. I'm sorry, let me just get there.
What
Now let me ask you the interesting question.
Yeah, but why
Yeah.
is it? Because it's on the line, like the signals are, most of them are over the line, so I would expect them to be sensed if the threshold.
Yes,
is
so
minimal.
thank you. So the next question I asked exactly right. So, all of these signals here, but I put some that are just unequivocally, but most of them, practically all of them are bigger than 2 millivolts, right?
Yeah.
And some of them are, and these are big and they're not sensed, right? And there are others that are, right? So how can that be? What, how would that work? What does the device know that we don't know? What is our, what are we not getting here? Okay, so I have your attention. This was the purpose of this slide, to motivate you. So this gets at the question, what is it that the device actually does? So it takes the signal, it amplifies it, so it can analyze it more, and it then filters it. I know you talked a little about filters when you talked about pacemakers, but we're going to come back to that. It then rectifies it. This is not an important step, but it confuses a lot of people. And just to show you what that means is that just means that all the negative signals are flipped positive. The reason for that is then you only need to look at positive voltages when you measure a threshold, and then you check to see if the rectified signal is bigger than the threshold. If you didn't rectify it, then you'd have to have both a positive threshold and a negative threshold. It's an extra circuit to build in. You don't want that. So this is a detail, but this filter is really important. The filter changes what the electrogram looks like. Now, it is true that this is the signal coming off the sensing channel. I didn't trick you in that regard. But the signal coming into the device is not the signal compared with the threshold. That is the signal after filtering. And I picked an electrogram from this company, which kindly, one of the few companies, I think it may be the only company that gives us both the unfiltered and filtered signals to see the difference. We can see that when there's undersensing, even though this particular signal unfiltered is larger than 2 millivolts, the filtered signal is less than 2 millivolts. So we need to understand the amplitude of the filtered signal before we make a decision, and before we, say that the device isn't working right. Now, here's another example. A key point is that when we remove what do filters do? They remove certain components from the signal. I'm showing you an example of what we call high pass filtering. We'll come to that in a minute, but high pass filtering means you throw out most of the signals that are lower than a certain frequency, and that's called the high pass frequency. This is 10 hertz. If you take an unfiltered sinus electrogram with ST segment, deviations, the first thing you get rid of, is the ST segment and the T waves. Those get really small. We want to do that. That's one of the goals of filtering. And in fact, we make them next to nothing when we filter at 20 hertz. But you can see the R wave has reduced in magnitude about 30%. On the other hand, the frequency content of ventricular fibrillation in polymorphic VT is much lower. So if we similarly filter ventricular fibrillation, polymorphic VT, we have now reduced the amplitude, by something like 70 or 80%. And so it's important that defibrillators generally can't operate with the same high level of high pass filters as pacemakers. Defibrillators typically operate in the, say, 12, 14, 15 hertz range. 20 hertz high pass filters, which one company uses, and pacemakers tend to use those. That's okay, because pacemakers don't need to see ventricular. I mean, they can't do anything about ventricular fibrillation. They understand it's not a big deal. But this is an important concept, that you change the amplitude of the signal by high pass filtering it. Why do we filter signals? And I know you saw a slide just like this in your pacemaker lecture. The idea is very low frequency signals are typically T waves or not cardiac signals. Very high frequency signals are not cardiac depolarizations. A real problem for the subcutaneous ICD is that the frequency content of signals recorded far from the heart, right, is always lower than those recorded near from the heart. And this has to do with the physics of both the physics of the distance from the heart and the separation of the electrodes. The basic idea is the farther apart your electrodes, the longer it takes from the signal to get from one to the other. And the duration of a signal is a rough measure of the inverse of the frequency. So VF, so signals coming from the surface of the body have much lower frequency. And that's a real problem. It was one of the reasons that T-wave oversensing was a challenging problem for SICT, because they couldn't just use frequency to separate the two. This is a busy slide. I don't want to spend too much time on it, only to make the point here that if you're recording from inside the heart, the signals are big and short, right? Those are high frequency signals. If you record from large, widely spaced electrodes far away, the signals are smaller, and they're longer, which means that they're lower frequency signals. And then also to remind you that in a defibrillator, the sensing signals are either off the tip electrode and an electrode close to it, either the shock coil or a dedicated ring electrode used for sensing, as in pacemakers. But the defibrillation signals are what we call the far field signals. That means they're not close to the heart. That typically means one electrode is far from the heart. And so, for example, a common one would be the signal between the surface of the generator housing, which we euphemistically call the can, and the right ventricular defibrillation coil. And this is good for telling the morphology of signals. As we'll see, it's not as accurate for determining timing. Now, I want to separate the concept of sensing from that of arrhythmia detection. Arrhythmia detection is the process by which ICD algorithms analyze a series of sensed electrograms, and they classify the rhythm, right? And then determine if they should deliver therapy. Now, this diagram has a lot of arrows, and nobody can ever get a lot of a lot of arrows down without staring at it for a long time. But I want to just walk you through the key points. Once we exceed the sensing threshold with the filtered signal from that previous slide I showed you, right? The device has an initial screening based on the rate of the signals or the intervals between them, and the duration. In other words, is the rhythm fast enough and long enough that the device should pay attention? And I know Dr. Pillow talked about this general concept. There is then the option to what we call analyze the rhythm and determine is it VT or SVT. It's what you do as doctors when you analyze a tachycardia. And you could, some defibrillators also apply extra rules to say, are some of these signals not really cardiac signals? And at that point, the type of therapy to deliver it is selected. If it's appropriate to deliver the therapy, it's delivered. If it's anti-tachycardia pacing, the therapy is delivered immediately. If it's a shock, right, well, then you know we have a 10-second delay time, right, to charge the high voltage capacitors. And in those 10 seconds, at the end of that, the device makes a go, no-go decision, right? Is the arrhythmia still present? And it does that pretty quickly. And this can be a little trigger happy because they don't want it. You don't want to miss real ventricular fibrillation from undersensing. And if the arrhythmia is still present according to the device, then you deliver the shock. After that, the device analyzes the rhythm. We call that a redetection period, and it looks to see if the tachycardia is still present. If so, it goes through some abbreviated version of this same cycle. If it's not present, the device does nothing but stays alert for the possibility of the arrhythmia being there and coming back, that it missed it, until it has some rule that says, I've done this long enough, I'm confident the arrhythmia is all gone. We call this episode termination. It then goes back to its original rules where it has to be woken up by these gatekeepers of, is the arrhythmia fast enough for long enough for the device to originally pay detection? Now, I pay attention. Now, I'm not expecting you to remember all that, but I want to have you get the idea. There are quite a few steps in that sequence. And if you really want to understand why devices do what they do, we have to be able to consider what each step does. Now, I also know Dr. Pillow talked to you a little bit about programming, but let me kind of give you, from a technology perspective, my sort of high-level view about that. So the prime directive from our TV show Star Trek from defibrillator programming is to detect and treat life-threatening VT and VF accurately. If we don't do that, nothing else matters. However, the second principle of ICD programming that has always been around, but has gotten increasing attention in the last 15 to 20 years, is to minimize shocks that we deliver patients unnecessarily, of course, without violating the prime directive. And that's because shocks reduce people's quality of life. They always involve engaging the medical system and increase the cost of care. And there may be variants, and of course, they use up device battery. So, as Dr. Pillow reviewed with you, we have some programming strategies for shock reduction. We want to make sure that the initial detection of arrhythmias lasts long enough that we don't treat arrhythmias that are going to stop on their own. We try to program a fast VT detection rate, or at least as fast as is safe without missing VT, because in general, slower tachycardias are well tolerated and they're more likely to be SVT. We apply SVT-VT discriminators to the extent they can be done accurately, because we do them to not, we don't want to treat SVT. We use anti-tachycardia pacing when appropriate, because that allows us to stop arrhythmias painlessly, and it allows us to do it with a low energy consumption. We generally use strong shocks because we generally use strong shocks because the risk of giving a stronger shock versus a weaker shock is minimal. And because defibrillation is, we'll get to this. I'm not going to discuss this, but you may have heard in other talks that defibrillation is always probabilistic. And the goal is to have to deliver a shock that is at a very high point on the defibrillation probability of success curve, so that you only deliver one shock nearly all the time. And then finally, if we have enhanced sensing features to minimize the chance of not detecting signals we don't want to, we should use those. So what are SVT-VT discrimination algorithms? SVT-VT discrimination algorithms are that element of arrhythmia detection that explicitly classify tachycardias as VT or SVT. Now, it turns out I've been working on SVT-VT discrimination algorithms since I was very small. No, actually, this was my younger son when he was very small, but almost 30 years ago, it turns out. The first paper came out that demonstrated, right, the goal of SVT-VT discrimination algorithms to prevent inappropriate therapy of SVT. And a few months later, I published a follow-up paper pointing out the main risk of this is that you can withhold or delay life-saving therapy from VT. And while the details of the algorithms have changed, and why some of the best modern work on SVT-VT discrimination has come from those of you in the audience in Bordeaux, for our students, these basic principles remain the same. We want to reject SVT, but not miss life-threatening VTs. So when we think about SVT-VT discrimination algorithms, as doctors, you have been taught to do this. And you've been taught to do it using the surface ECG. And there are various rules you may have learned to tell VT from SVT. For example, if the QRS complex is wide, or if it has certain morphological features. So for example, the absence of an RS complex in any precordial lead, or Q waves in certain leads. And we have these types of rules. But if we think about the structure of an SVT-VT discrimination algorithm used for ECGs, they have three key features. First, there are individual rules that are applied in some ordered sequence. Secondly, most of these are what in device world we call single chamber rules. They only look at the QRS, and only one is a dual chamber rule. That is, right, is the atrium and ventricle or the dissociated, or the P waves dissociated on the surface ECG. And the third is that the single chamber algorithms analyze the QRS morphology on the surface ECG lead. And importantly, we give priority, right, not to the dual chamber criterion, finding the P waves. And the reason we don't is finding P waves during wide complex tachycardias can be very difficult if you're an honest electrocardiographer. Now, when we think about the structure of defibrillator dual chamber SVT-VT discrimination algorithms, they have certain similarities and key differences. Similarly, discriminators are applied in some ordered sequence. Sorry about that. Differently, dual chamber discriminators take priority. And in this particular company's device, I picked it because it's simple and you can follow it. The first step is the ventricular.
I really enjoyed that you selected Boston Scientific. Sorry to interrupt you, but this morning I gave the students 266 VT episodes from dual chamber Boston Scientific devices.
Good. Okay.
And of those 266 episodes, there are actually 20 which are SVT. So 20 are inappropriately classified as SVT, so inappropriate therapies. And the challenge is, and they have until Monday afternoon, so I don't know if they succeed, but then I will show you how I did it. The challenge is to make an algorithm which is better. Because I have all the signals, all the algorithms, and all the markers in a digital structure. So this is really interesting. Yeah, it's really interesting. I did not explain to them how Boston Scientific works, how they do it. So please go ahead. That's really falls nicely within our project.
Okay, good. Well, this is what we call serendipity. So we'll go through it in. So the first step, though, right? The assumption is that atrial sensing is reliable, and you can see the P waves in a dual chamber defibrillator, whereas that's not your assumption on the surface ECG during wide complex tachycardias. I'm not going to spend much time on this, but you notice they don't say ventricular rate is greater than atrial rate. They say ventricular rate greater than atrial rate plus 10 beats per minute. The reason for that, and this is a technical point, and it's not something you're going to need to know to solve Dr. Strick's diagnoses, but the reason for that is that they're hedging their bets about exactly how good atrial sensing is. And there are various reasons you might not sense a atrial electrogram during tachycardia, including the so-called post-ventricular atrial blanking period. And so they've put in a little fudge factor. Every company has some version of this fudge factor, and it can lead to some pretty confusing cases on this boundary. But we're just going to say ventricular rate greater than atrial rate. And the second key point is the primary single chamber discriminator is the shape of the electrical signal. Like, does it look like the sinus beats or not? And then finally, if it doesn't, they use another analysis based on intervals, and they say if the atrial rate is really fast, and we think this is atrial fib, the ventricular rate is irregular, and it's irregular enough, then we know that rapidly conducted atrial fib can have some aberrancy. And the way Boston set up its nominal features for electrogram match is so strict that they added this in. If they had actually set their nominal feature the way those of your faculty at Bordeaux had determined was optimal, they might not actually need this feature, but we're not gonna go there today. Okay, what happens when we click? So what are the single chamber discriminators used in SVT discrimination? Well, without spending too much time on details, one is a regularity criterion, which for whatever reason is called interval stability as opposed to regularity. That is, are the intervals, but it means are the intervals regular? It doesn't have anything to do with hemodynamic stability. And a stable or regular rhythm, right, would be monomorphic VT, and an irregular rhythm would be AFib. Abruptness or sudden onset in the ventricle is designed to discriminate sinus tachycardia from VT. The general idea is VT starts abruptly and sinus tachycardia accelerates gradually. The third, what we call it, is the shape of the signal, right? And this is capable of discriminating, right? Wide QRS complex, different looks different. You know, that can discriminate any type of VT from SVT. Now, as a general rule, there are many problems with single chamber ventricular sudden onset discriminators that can make big mistakes. And the other key point about a sudden onset discriminator is that if it misses the onset of VT, it will never detect the rhythm. And for all kinds of good rhythms, you should never program a ventricular sudden onset discriminator without a priest, a social worker, and you know, and an act of you know, and an act of your, you know, at least local legislature. And your primary, there are times, not too often, there are times though when when irregularity discriminators can be useful, although they have some risks. And the primary discriminator we use is ventricular electrogram morphology. So here is, here's an example of a hypertrophic cardiomyopathy patient with a single chamber defibrillator. You know, I lost my, oh, there's my picture for you guys. Sorry about that. Let me just get this back and I will. I wanted to see you guys. I was getting lonely. Wait 1 sec. All right. So now we'll ask one of the students. This is still not working. I apologize for this. Give me, it's going to work in a minute. All right. Is this VT? Whoa, that was bad. Is this VT or SVT? How would you know? Well, you can say, Chuck, in a single chamber device, you can't tell for sure, right? But suppose I told you this is, go ahead, I'm sorry.
No, I just want to say the onset seems relatively abrupt, and the
Right.
morphology changed at the same amount in time. Like it's not much different, so I don't know if this is sufficient to discriminate it, but it definitely looks different from the second to last VS one.
Yes, and you have identified all the key characteristics of this slide. And I'm sorry, that was who? I apologize.
Daniel, yeah.
Daniel, okay, good. So Dan, you've identified all the key characteristics here. Now, if you look at, now if I really push you and say, what's different about the shape in sinus rhythm versus tachycardia? What's really different is the amplitude, right? I mean, the signal is just as, not any more wide or narrow. It's got a big positive deflection, right? A slightly smaller negative deflection. And the shapes of the positive and negative deflections are about the same. In fact, if you took this put it on top of it and just stretched it up and down, right? I mean, made it a little taller, like in a funhouse mirror, then they would match. So a key point is that amplitude changes happen all the time for electrograms during tachycardia, far field electron, and you should never think about that as a morphology change. And in fact, one company, actually it was Boston Scientific, didn't take that into account with their first morphology algorithm, and it was a catastrophic failure. So this is an abrupt onset SVT. Now your question is, in a single chamber device, how do you know it's really SVT? How can you ever be sure? And the answer is, well, usually you can't be sure, but in this case, I did this in the electrophysiology lab by turning on rapid atrial pacing at exactly this point. So I can be pretty sure of what was happening here. But that's a good point. In a single chamber device, it's hard to be 100% sure. So the next question is, which single chamber discriminator would correctly classify this rhythm as SVT? Well, let's go through it, and you guys call out. You said the onset is abrupt, so, and that's our sudden. If onset is sudden, how does the onset stability classify the rhythm?
It's not a good classifier.
It would classify it as, onset classifies gradual as sinus tach and rapid as VT, abrupt as VT. So onset would get this wrong. What about stability, which we mean interval regularity, right? Would that classify it correctly or incorrectly?
That would classify it correctly, right?
So
Well,
let's think about it.
You could not say it because also VT could be relatively stable.
So, right, the stability criterion is exactly right. It says that a stable or regular rhythm is VT and an irregular rhythm is AF. course, rapid atrial pacing or atrial tachycardia, sinus tach is also regular. Morphology, of course, got this right. How do I know that? Oh, I'm sorry. Did I get this right? I know, oh gosh, you know what? I don't show it to you and I apologize. But take my word for it. I left out a slide showing the morphology match points, but morphology did get this right. And of course, atrial versus ventricular rate is not a single chamber criterion. So here's another tachycardia. Is this VT or SVT? Anybody want to say?
Looks like SVT.
Yeah, SVT.
And that's because
Morphology
the
mostly.
morphology looks the same, right? That would almost be true. But there is an important rule. And the moral of this slide, which you'll now remember, is you should never make a global decision, like what is the cardiac rhythm and analyze the morphology when you're looking at the near field sensing electrogram. The field of view of and it was a little, I did actually label it here. This is as the sensing electrogram, but I didn't emphasize it, right? Because, I can be a little sneaky. But the key point is that when you have the local sensing electrogram, you can't tell if it's VT or SVT. For example, if you look at a pacemaker, electrode during a tachycardia, or you're in the electrophysiology lab and you look at the signals coming off your closely spaced electrode in your mapping catheter, you don't make the diagnosis based on the morphology of that electrogram. And so we can't really say anything about the morphology of from a single chamber, from a local electrogram, as opposed to the shock channel. Here, for example, is the actual recording from the dual chamber defibrillator. And we can see, to make this point, here's sinus rhythm. Here are a few beats of atrial tachycardia, right? The P waves precede the QRS, and there's and then when the atrial tachycardia stops, we resume sinus rhythm. And here, of course, is VT with more ventricular signals than atrial signals. And on the local sensing bipole, they all pretty much look the same. So don't make a global decision based on local electrograms. And the key idea is we can use far field shock electrograms or the surface ECG to make morphology decisions, right? Don't use the local sensing electrogram, which is great for timing, but not good for morphology. Okay, so we've been going a little over an hour. Are you guys all good for another hour, or do you need a break?
No, it's okay.
Okay, good. Well, I have a drink so I can so I don't get too hoarse. So I want to spend a minute then, since we've discussed single chamber morphology discriminators. How do morphology discriminators work? Well, they all work, while there are technical differences. They all have these common characteristics. First, they store some representation of the sinus or baseline rhythm electrogram. They then, after they have stored that template, they then look at a series of shock electrograms, far field electrograms, during tachycardia, and they store those. Might be 3, it might be 8 or 10 or something in that number. They then have some method for telling you how to line up the the tachycardia electrogram with the template electrogram, right? Because if you don't line them up right, you can't compare them. And the methods of lining them up differ among different companies. That's actually quite important. Once you've lined them up correctly, and if you don't line them up correctly, that's a major source of error in these algorithms. Then you compare the shape of the unknown electrogram to the known electrogram, and you see if it exceeds some match threshold. And if it doesn't match very well, you call it a ventricular beat. If it matches really well, you call it a supraventricular beat. And then if enough of the beats match, you call the rhythm supraventricular. And typically you only need a few beats to match, like 3 out of 8 or 3 out of 10, because it's very rare for 3 or 4 VT beats in a ventricular tachycardia or ventricular fibrillation to match a sinus beat. Either they're all going to match or none of them are going to match. So having said that, let's put your skills to the test. Here's an electrogram that we in the atrium, we can see that it's atrial fibrillation. Here is an electrogram in the ventricle. And here are your match percentages. And the match percent needed for a match in this company is 70%. So let's have one of the, can I start picking on some of the other students? I'm pretty mean about doing that to make sure, you stop Facebooking, but or Instagramming or, whatever, Snapchatting or whatever the app is you use in France. Sorry, those are the ones we use in America. So is this VT or SVT?
You can ask anyone. You have now a lot of young electrophysiologists
Okay,
coming from everywhere in France. So you can ask.
So Sarah, can we put you on this hot seat for a minute? Is this VT or SVT?
Okay, to me the rhythm is irregular. The algorithm matching is close to SVT. I go for SVT.
Right, so excellent. Couldn't have done better myself. So this is conducted atrial fibrillation, right? And it's correct because, and we see, right, there is some beat, and even in this SVT, right, we see there's beat to beat variation electrogram amplitude, but almost no variation in electrogram morphology, right? All right. Oh, gosh. Zoom, okay. So what about this one? Can we get a different volunteer here? Is it Moa? Is that your name? Do I have it right? You want to try this one?
I can.
Hey, I'm finding it quite difficult to see because my internet is super bad.
Oh, I see. Okay. That,
Sorry.
that's an excuse we don't have an in-person conversation, right? Okay.
I know.
Who's going to help Moa out? Anybody want to volunteer? Hugo? We got 2 Hugos.
One is from Canada and one is from France. I think
Yes,
we
let's
should
go to
challenge both.
Canada.
Okay,
Okay.
Canada.
Is still SVT, probably AFib, because it looks irregular to me.
So, okay, but what does the defibrillator say it is?
It says VT, and it's yeah, it says VT.
So the defibrillator, so again, great work. So what we have here, right, is is an irregular rhythm with beat to beat variability in amplitude, but none in morphology. And we notice, and after a pause, right, the amplitude's lower. Here the device delivers unnecessary therapy. And we notice that although the defibrillator gets it wrong, it doesn't get it terribly wrong, right? The match percentages, it needs 3 out of 8 to be above 70%. And here 1 is 70% or 70% longer. And 4 of them are 67%, right? And so your confidence in the morphology algorithm's decision should be related to the match percent, provided that the alignment is correct. And does that screen look blurred? And mine looks blurred when I do this. I don't know if
Yeah,
it's,
it looks blurry. Yeah.
it's like, you know, this is a zoom feature. If I do it in PowerPoint, it's not blurred, but we're just going to keep going. It may have to do with, but
No,
the
it looks
key
fine.
point is if you get 70, if you get a match that's only 1 or 2% below the threshold, you should be, you know, think to yourself that decisions in medicine are rarely digital, right? Now, another key
For
point.
Medtronic, it sometimes gives me chest pain if I look the wavelet at work.
I'm sorry, Mark, say that again, please. I didn't.
You must agree that if we look at Medtronic decisions, sometimes it's just give you a bit of chest pain looking at the wavelet at work. I mean, if we look at the correlation in our heads, it's better than 70%, but still, it's making this decision that it looks.
You know,
doesn't match.
Wavelet was a great algorithm. This is a good example of not updating your technology. You know, Wavelet came out, you know, the first paper on Wavelet was published in 2002. And it identified all the major failure modes of the algorithm. The algorithm remains unchanged in transvenous devices 20 years later. If you use the same software on your computers that you used 20 years ago, it really wouldn't be what we expect, right?
Of course.
So I think what Mark is saying, if I understand it correctly from chest pain, is that it's difficult to understand the decisions that there are multiple failure modes, that it just gets wrong, that it shouldn't. That your eye is much better at detecting it, classifying. Is that
Exactly? Yeah, we would expect some adjustments.
We would expect some improvements in 20
wavelets.
years.
Yeah.
Yeah. Okay. This is not okay, but we're here to. So we're not going to get me started on that. I've written many memos about that in the last 20 years. Let me now turn from single chamber discrimination to dual chamber discrimination. When it comes to dual chamber discrimination, as I've discussed, the most important part, you know, and the single most important step is comparison of atrial ventricular rate. And the reason for that, right, is that if the ventricular rate's faster than the atrial rate, and this is done right, and actually St. Jude means if it's faster by more than a little bit, then we just deliver VT. We don't just deliver VT therapy. We don't think about it. On the other hand, if it's a 1-to-1 tachycardia or atrial rate's faster than the ventricular rate, then we have to think about whether it's VT or SVT, and there are a bunch of rules to apply. And without getting into the details, the key point is that each of the individual discriminators, single, dual chamber, and Abbott has just a lot of these discriminators, classifies a subset of the tachycardias as VT or SVT. And then the final classification of the whole algorithm depends on both the individual discriminators used and what their logical connections are. Okay, now this is a bit of an advanced question, but here are 2 episodes of inappropriate therapy of supraventricular tachycardias. We use SVTs in the broad sense, not the electrophysiologic sense. You can see this is atrial fibrillation that's treated inappropriately. And this is sinus tachycardia that's treated inappropriately. And my question is, which of these could be corrected by a morphology discriminator? This requires a little thought. How would you think that through? Well, let's work through it. What's going on in the atrium up here? Is sensing appropriate? Is there oversensing or is there undersensing? And here's the marker channel. There's an atrial marker channel on top. And so we want you to pay attention to the atrial marker channel. Compared to all the ventricular electrograms, are there as many markers, too many markers, or too few markers? How about the Hugo from France?
So there is AF undersensing.
Yeah.
I'm sorry, could you say that again? I didn't hear you.
Yeah, I suspect AF undersensing.
Exactly right. This is atrial undersensing. Let's go for the lower channel. What at lower tracing? Here's the marker channel. What is atrial sensing appropriate? Is there oversensing or undersensing? Well, this is sinus tachycardia, right? This is a P wave. This is a QRS. What's this? We call this the far field R wave, right? It always lines up with the R waves on the ventricular channel, and it is the representation of ventricular signal recorded on the atrial electrogram, right? It's not sensed here, but it is sensed here. So we call this intermittent what? Oversensing, right? Too many markers, more markers than P waves, intermittent atrial oversensing. This device, how does the defibrillator classify this rhythm? A greater than V, V greater than A, or A equal V?
V greater than A.
Say one more time, please.
More V than A, so V greater than
Yes, really there are more A's than V's, but the defibrillator says more V's than A's. What does a defibrillator do when it sees more V's than A's?
it goes directly to a diagnosis of VT.
Right. Here, how does it classify the rhythm? It classifies the rhythm as,
A greater than V.
and what does it do when it sees more A's and V's?
It uses the other discriminators.
It uses other discriminators, right? So this gets to a key point, which is if you have marginal atrial sensing, oh, I'm sorry about this. If you have marginal atrial sensing, right, you should always err on the side of oversensing, because in the worst case analysis, that can be cleaned up by single chamber discriminators if you have sinus if you have SVT. But if you undersense the atrial signals, then there is no chance to get the arrhythmia diagnosis right. And undersensing in atrial fibrillation is a cause of errors in dual chamber algorithms. Okay. So I said all that to you, and this slide just says it in writing. All right, I want to spend 1 minute about magnet mode because we put magnets on pacemakers and defibrillators. Why do we do that? Well, what is the historical context? You know, even before I was born, and there were pacemakers, before I got into this, right? There were original pacemakers that didn't have telemetry. You couldn't put a programming one on and communicate. They had the devices, but no method of communication. And magnets were used to alter the pacemaker functionality to assess battery capacity. Now, of course, we don't need them for that anymore, right? Today, right, pacemakers will pace asynchronously when you put a magnet on it, and and ICDs inhibit tachycardia therapy when you put a magnet on it. And this is useful. And although details differ among manufacturers, exactly how pacemakers pace, although they pace asynchronously, they may do other things. Magnets can be used conveniently. For example, you can put a magnet on a pacemaker during electrosurgery, right? And the defibrillator will, on a pacemaker, and the device won't be inhibited by the oversensing of electrosurgical signals, and the defibrillator won't detect those as ventricular fibrillation delivers shocks. And it can also be used for various pacemaker troubleshooting. If you don't have a program, and a programmer available in emergency rooms. And since this is not a pacemaker lecture, we won't go into that. The strength of the magnetic field required to initiate magnet mode is mandated by international convention at 10 Gauss. So if you apply a 10 Gauss field to a pacemaker defibrillator, it needs to go into magnet mode. To give you an idea, the Earth's magnetic field, depending where you are, is somewhere between 1/4 of a Gauss and 3/4 of a Gauss. And a MRI scanner, when you hear it's 1.5 Tesla, a Tesla is 10,000 Gauss. So a 1.5 Tesla scanner is 15,000 Gauss. What happens inside the device when you apply a magnet? In older devices, there was an actual set of magnets in there that would move, contact each other, and close an electrical circuit. And these were called reed switches. Almost all manufacturers, except for the current Chinese manufacturer, no longer use this technology. They use Hall sensors. What is a Hall sensor? And you guys don't really need to know this, but the Hall effect is an effect that happens when you apply a magnet to a conductor that is conducted in an electric circuit. And when electricity is flowing through the conductor, if you apply the magnet, depending on whether whether the moving charges are positive or negative, and we all know that the moving charges in conductors are electrons. This is the actual first proof that the real moving charges in conductors were electrons. That the magnet will separate, because magnets apply forces to moving charges, that it will separate the positive and negative charges, and there will be a voltage induced across the conductor. And that voltage is measured, and when that voltage is measured, the pacemaker enters magnet mode. Why are Hall sensors preferable? They can't be damaged by strong magnetic fields. You know, these can be smashed by MRI scanners. They can be turned off, right? You can just turn the current off in this circuit for MRI scanning, make the device MRI conditional. And if we wanted to change magnet mode, and people are thinking about this today because we have time later, we can talk about all this. You may have, I'm sure it's made the press in Europe, iPhones and various other consumer devices with strong neodymium magnets affecting pacemakers and defibrillators, that it is possible to get a differential response to magnet polarity depending on the direction of the voltage induced by the magnet. All right, I'd like to turn now to pacemaker leads. And when I was very young, there was a character on a television show we watched in the United States called Saturday Night Live. Father Guido Sarducci was the chancellor of what he called the 5-minute university. And he promised that in 5 minutes, you learn what the average college graduate remembers 5 years after graduation. So for example, a course on economics would be, there's supply, there's demand. You can Google that, you can look this up on YouTube. They're actually pretty funny. So the 5-minute course on lead design is, leads consist of metal conductors that run through them and plastic insulators that surround them. But of course, I have almost a half hour left. So in a little more detail, the metal conductors transmit the low amplitude, that is millivolt level cardiac bioelectric signals to the sensing circuits, and they send the voltage or close to 1,000 volt level defibrillation pulses to the heart. The plastic conductors prevent non-cardiac signals from entering the leads and therefore being transmitted into the sensing circuits, which of course get through the feed-throughs. They ensure that the pacing and defibrillation signals reach the heart without being dissipated in the tissue. And they protect the conductors against corrosion from the body's biological environment. Now, when we think of the relationship of conductors and leads, there are various ways you can package conductors and leads. And for the purpose of this lecture, I'm just going to focus on defibrillator leads, which consist of coil conductors that go all the way through to the end and allow us to actively fix or screw the lead into the tissue, and cable conductors, which are smaller and can be used either for pacing or defibrillation. So with a little more detail, the primary pacing metal is an alloy called MP35N. MP stands for multi-purpose, and 35N tells you it's got 35% nickel. This was not designed by pacemaker, engineers. It was designed for use in oil rigs in the Gulf of Mexico, where we, pump oil in the United States. And it has three key characteristics. It's light and strong. It's corrosion resistant in a saltwater environment like the body. And it's fatigue resistant against bending in Atlantic hurricanes. So, or in shoulder motion and, intracardiac motion. Cables are mostly MP35N, but the defibrillation cables have either a silver or platinum core, now mostly today. Why is that? And that's because the electrical resistance of MP35N, while good enough for sensing circuits, is way too high to allow efficient transmission of defibrillation energy. So to give you an example, if we, a typical resistance of a defibrillation coil in a circuit might be 30 or 40 ohms, maybe 50 ohms in a pacing coil. In a cable might be 20 ohms, but once we put one or two silver strands right through the middle, the electrical resistance goes down to 1 ohm. And we'll learn in a minute that resistance is what determines power dissipation and energy dissipation in the lead. And when we're delivering high voltage electricity and a lot of energy, we don't want it to be dissipated in the lead in the body. So that's the construction of the conductors. Now, how do you break conductors? Well, you break conductors by bending. And we measure stress on the conductor because the likelihood of breaking depends on how much stress is on the conductor and how many times you bend it. The problem is it's hard to measure stress forces in the human body. Luckily, we can calculate stress from geometry. The key, the key mechanical engineering point is that stress depends on the curvature. Curvature is defined as the inverse of the radius of curvature. So here, if we have a 1 centimeter radius of curvature, the inverse of that is, 1 centimeter to the -1. If we bend the lead with a 1/3 centimeter radius of curvature, then curvature is 3 times as great, and the stress on the cable, on the cable and coil is 3 times as great. Because of this direct proportionality between stress and curvature, we could, in principle, calculate the stress on cables that are implanted in people when they move their arms around. It's incredible for the 50 years people have been building leads, nobody's done this. But I'm presently involved in a project where we're taking biplane fluoroscopy of leads with shoulder motion, so we can actually understand the stress on leads during use conditions. So defibrillator and pacemaker manufacturers have some actual use condition data to know what their leads need to stand up to. Okay, what about the insulation? Sorry about that. Well, there are a couple of different kinds of plastic that are used, and I want to demystify these for you. First, silicone. That's that stuff that's in the soles of your shoes. It's very soft, and the great thing about it is biologically inert. The bad thing about it, just like you wear down the soles of your athletic shoes, right? If you use them, if you run too much, walk too much, it's mechanically weak. There are these blue fluoropolymers. This stuff's a lot like Teflon, but it's a slightly different cousin. Ethylene tetrafluoroethylene, if you want to know what the ETFE stands for. And in this company's devices, they're blue. And this prevents the cables from cutting into the soft silicone. It keeps the cables from unwinding. It also makes it easier just to build the leads and pass the cables through there. And on the outside, we often have a more resistant, tougher polymer, so that the silicone, which is biologically biologically inert and very flexible, but not as strong and not as tough, can be coated by a tougher polymer. Now, if we say, how do leads fail? Well, either the insulation fails or the conductors fail. Insulation fails by chemical degradation. The silicone undergoes some type of chemical reaction, or not the silicone, but some other polymer undergoes some type of chemical reaction, or it gets mechanically beaten up, and that's mostly silicone. Here you can see what we call as cold flow pressure on a silicone lead has smushed away the silicone. So it's either mechanically deformed by pressure or just by wear and tear. So now, one of the measurements we use for lead integrity is electrical impedance. And here's an example of a lead conductor fracture, and it's particularly thought originally to be useful for leads, that in fact, the conductor impedance goes to a very high value, telling you that that circuit is disconnected. And that indicates that occurs, the only way that can occur is if the conductor is fractured. Well, what exactly is lead impedance? I asked this to our fellows, and I won't ask it of your students, and I get a lot of interesting answers. But most of our fellows understand that current is a measure, right, of the number of electrons flowing through a wire at a given time. And the voltage, some of our fellows know, is the actual energy of each electron, or potential energy of each electron flowing through the circuit. Impedance does not have a direct single physical correlate. It's defined simply as the ratio of voltage to current. In fact, impedance has two different components. The common one that we think about in direct current circuits is what we call electrical resistance. Resistance is what dissipates energy in a lead. So energy dissipation and heating is due to resistance. There is another component of impedance in it, however, which occurs in leads that have more, in circuits that have more than just resistors in them. For example, let's say you're charging the shock capacitor of defibrillators we've talked about, right? We have current flowing into the capacitor. We have voltage that's applied to the system to do that. but instead of dissipating energy, we're actually storing energy in the circuit, right? So impedance can relate either to energy storage, and in MRI circuits, right, we store the circuits in inductors, but it can either relate to electrical or mechanical energy stored in this, while we're storing energy in a circuit, or it can relate to energy being dissipated. But for the most part, in leads, we're going to just talk about energy dissipation and resistance. So here, for example, is another lead that broke, right? And I asked the question, how can that be? This is one of my leads. And you can see if you take it apart, right? Impedance is completely normal. You can see that the conductor is completely separated, the helix, right? And if we remove the plastic, there's just nothing holding it together except the stylet through there. But the impedance was was completely normal. Why is that? Because in real life, most of the time, the lead body will constrain the fracture faces to stay next to each other to maintain electrical continuity. And I just, I just want to show you this, since this is one of my current ongoing research projects, where we have been crazy enough to try and look at the relationship between the mechanical structure in leads, the electrical signals that fractures induce. And here, for example, we see the normal electrical signals. This is our simulated cardiac electrogram. And these signals occur every time we bend the lead, and that's from the beginning of a fracture. And the way we did that was we put the lead in one of those testing apparatuses, except instead of showing you the testing apparatus in air, we waterproofed it and dunked it in a saline bath. And then instead of taking a little segmental lead, we took a whole lead, and we connected it to a defibrillator, connected the electrical circuits, and we recorded the electrical signals out of there. And we made a lot of mistakes doing this, but we finally got it right. And so, for example, here you can see a completely broken lead. I mean, but you can see that when we don't bend it too much, there is good electrical continuity. When I apologize, these should be the other, I'm sorry, when we don't bend it much, there's no electrical continuity. When we bend it, we smush the conductors together. And so the impedance can vary, right, depending on how much the lead is being bent at the time you measure it, between completely normal and completely abnormal, right, very high. And when we stop bending the lead, the electrical signals become normal again, even though they're just crazy electrical signals while we're bending the lead. So diagnosing conductor fractures can be pretty tricky, and we can have complete breaks with next to no impedance changes. So this is one of the reasons that Dr. Pelot, Dr. Bordechar, and Dr. Strick have written a number of papers emphasizing the importance of reviewing the electrograms, even just random electrograms that come through on routine transmissions, to make sure that leads aren't fractured, even though the impedances are normal. Impedance is also usually normal when insulation is broken, and we can go through details of why these are. But here's an example of one of my leads for Mark and Sylvain and Pierre. This is a tendril lead, right? And we've seen a lot of insulation get broke on those, and the impedance trend is completely normal. In my last 15 minutes, I'd like to say something about defibrillation waveforms. And are you folks still awake? Anybody still awake there? Should I have a quick sleep awake check? Okay, thanks. Okay, so
It's okay.
Okay, what are defibrillation waveforms? Waveforms are the temporal pattern of the shock. So, and it's measured either as voltage or current how we plot that over time. And in green, we have the shape of a typical defibrillator waveform, which is the waveform you get when you discharge the shock capacitor, as we talked about earlier. When you remember I said a capacitive discharge gives you an inverse exponential curve. Instead of letting that curve run out infinitely, we truncate the curve after a period of time and flip the polarity. The slope of this curve, or the time constant, right, we remember depends both on the capacitance and the resistance of the shock pathway. But let's say for a given lead, the shock pathway is fixed. Let's say it's 50 ohms. So if we attach a large capacitor, then we will have a slower discharge. And if we attach a smaller capacitive waveform, right, then it will discharge faster. So by choosing the capacitor, we influence how fast the shock is delivered. How fast should a shock be delivered? This is a good question. So why do we care about defibrillation waveforms? Waveforms describe the strength and the duration of the local electric field at a cell. So for example, this is a stylized example of, and I know you had a lecture by Dr. Efimov, and I don't know exactly what he covered, and Dr. Efimov is a genius, and I'm not sure exactly what he covered on defibrillation, but he probably talked to you something about electric field strength. And field strength is typically very high at the shock electrodes, and then as we get into cardiac tissue, it gets lower. So here, for an example, is where we deliver 800 volts between a RV defibrillation electrode in a can, and the average field strength, that would be the slope of this line, is about 3 volts per centimeter over the heart, even though it's very strong at the beginning and the end. What can a cell do? The key point is that if we look at the shock's cell membrane voltage, the change in membrane voltage occurs only as fast as the partially responsive sodium channels in a fibrillating in a cell during VF can respond. So you can apply all the voltage you want because electronic circuits can apply voltage very fast. But it doesn't matter if you apply, and this is an experiment where the voltages were lower than in typical defibrillator shocks, but you can apply 200 volts, 400 volts, 10,000 volts. The defibrillator will apply that voltage, but the membrane cannot respond any faster than its biological time constants determined by the ion channels in the membrane. We call the time at which the cell can respond the membrane time constant. And there's a membrane time constant for completely repolarized cells, which is one we use for pacing, and a membrane time constant for partially depolarized cells is what we use for defibrillation. And the goal, if we of optimizing a defibrillation waveform, is to approximately limit the shock strength, to approximately limit the time of your defibrillation pulse for the first phase of defibrillation to the amount of time it takes for the cell membrane to get to whatever its maximum value is. Once you have made a change in the cell membrane, as much as you can, as much as the cell membrane can do, nothing else is going to happen. And yet you are at best just wasting energy. And so shocks are most efficient when the time constant of the shock approximates the time constant of the cell membrane. I know you saw a strength duration curve when you studied pacing and had electron pacing. The question is, what is the optimal pacing duration? And you heard these, impenetrable terms, the chronaxine, well, the real base, right, which is the pacing threshold for a very long pulse, and the chronaxine, which is the time at which the voltage threshold is twice what it is at the asymptote, the real base. And you learn that was important because that's the shock strength that defibrillates with minimum energy. Another way to say that, that's the pacing pulse that it captures with minimum energy. Exactly the same thing is true for defibrillation. The reason we do this is the reason we do this is you want to match the waveform duration to the time constant of the cell membrane. Pacing uses very tiny capacitors, and the difference in voltage between the start and stop of the pulse isn't that much. So we don't really care about the waveform time constants for pacing. But the time constant for defibrillation is roughly 10 to 15 times the time constant for pacing, right? It's 3 or 4 milliseconds as opposed to 0.2 or 0.3 milliseconds. So we want to deliver pulses that are 10 or 15 or 20 times as long, right? 3 to 5 millisecond phase one duration. Now, the next question is, how strong an electric field do we need to defibrillate? Dr. Efimov may have covered this, but typically for biphasic waveforms, which are more efficient than monophasic waveforms, we need 3 or 4 volts per centimeter. Monophasic waveforms about twice as strong. To give you an idea, for pacing, you need about 1 volt per centimeter. Even though we deliver 10 million times as much energy in a defibrillation shock, the field strength required are only 3 times as big. Why is that? That's because in defibrillation, we have to have that field strength throughout the entire heart. And as Dr. Efimov probably told you, any place that you don't, if there's any place in the ventricle where you don't reach that field strength, then fibrillation will continue. On the other hand, in pacing, all you have to do is excite local tissue for a square millimeter at the tip of the pacing catheter, and then the heart's propagated impulses will do the rest. So waveforms are most efficient when the shock waveform duration and time constant is about the same as that of the membrane time constant. So how do we know how to set phase 2? Well, the current thinking is that the main goal of phase 2 is to get rid of the charge you deposited on the membrane at the end of phase 1. So whatever the, if in pink we see the estimated membrane voltage, phase 2 is customized to phase 1 ideally to get rid of that charge. And exactly how you do that and the math behind estimating this was worked out by several people, including Mark Kroll in the 1990s. And it predicts that, for example, that the most efficient waveforms for very big capacitors should have shorter phase 2s, for smaller capacitors that work faster, longer phase 2s. And the details are unimportant, but the idea is we want to get rid of this extra voltage because that's what contributes to refibrillation after a defibrillation shock. And as Dr. Efimov told you, most failed defibrillation isn't really stopping all the waveforms, it's reinitiating fibrillation. Finally, I'd like to make the point that we consider the polarity of shocks. And I suspect Dr. Ethema talked to you about his the work he did on the virtual electrode hypothesis of defibrillation. But one of the clinical implications of that, even if you don't follow all the math, is that in a biphasic shock, if you make the right ventricle anodal, that the virtual electrodes that you start in the tissue, and if you remember from I suspect Dr. Efimov taught you that virtual electrodes mean that if you have heterogeneous tissue, there are areas of opposite polarity that form distant to the electrode. If we make the RV plus positive, those waveforms collapse toward the electrode, cancel each other out, and don't refibrillate. The other hand, if we make the RV electrode positive, negative, I'm sorry, or the, I'm sorry, this is the RV being positive with the signals collapsing in. If we make the RV negative, that is the cathode, and I apologize for my error, then the virtual electrodes start waveforms that propagate outward into tissue and are more likely to refibrillate. So this is why all manufacturers either nominally program the RV positive, or for one manufacturer, the representatives all change the polarity, and you should never change the polarity of defibrillation shocks. All right, so let's test your knowledge. Let's have a vote. In comparison with electric field strength required for bradycardia patient, how strong is the field strength required for defibrillation? About the same, 50% greater, 3 to 6 times greater, 10 to 20 times greater, or 50 to 100 times greater? Who's been paying attention?
C.
Correct.
Few
3 to 6
times greater. Yeah.
Even though we use 10 million times the energy of a pacing pulse, we only need a slightly greater field because defibrillation is a global phenomenon and pacing is a local phenomenon. So I'd like to leave you with this thought. Mark Twain was an American 19th century writer, and in a book in which 3 of his favorite characters, Huck Finn and Tom Sawyer, and the slave Jim toured Europe and then went on to Africa, called appropriately for Americans, Innocents Abroad. They were staring at the stars over the Sahara Desert and trying to come up with a hypothesis for the Sahara Desert. And Tom says, theories don't prove nothing. They only give you a place to rest on in a spell when you're tuckered out. And there's always a hole in them somewhere, sure enough, if you look close. So I want to encourage you to keep poking holes in our theories and concepts of arrhythmia diagnosis and defibrillation. There are definitely better ways to build devices than we do today. There are plenty of holes in our designs and theories, and I hope I've done a little bit to encourage you about the scope of this technology, and the fact there's a lot more to be done in the future. And I hope you enjoyed this as much as my cat likes his frozen yogurt. And I'm just about on time. So happy to take questions,
Great.
jokes.
I will have a question on the polarity of the shocks. You would, if I understand, you will recommend anodal shock. And if there are different constructors where the nominal polarity is cathodal for the shocks, do you have an explanation for that first? And then do you modify systematically the polarity for this kind of device or not?
Right. So I think the question is, most manufacturers except Boston Scientific,
Yes.
all manufacturers have anodal shocks.
Yes.
every manufacturer has its quirk. Boston came out with a polarity. The polarity Boston uses and their circuitry was originally designed when they were a pre-existing company called Guidant. And nobody, this was before Dr. Efimov and others had shown that one, not that he had not only shown clinically, theoretically, but, all the available clinical data, although there's not all that much, show experimentally that anodal shocks are superior. So Boston devices should all be reprogrammed to anodal shocks. Now, there's another folklore or type of witchcraft in which, since all defibrillators give you 6 or 8 shocks and people get bored, they say, well, if the first 3 shocks don't work, I'm going to switch the polarity and see if that helps. This is a misunderstanding of defibrillation data based on some early studies where people claim that altering polarity improved defibrillation. Those conclusions were based on not understanding statistics correctly. And if anyone is interested, I can pull some slides to show you that. But the basic concept is that defibrillation is always probabilistic. So there's always some chance you're going to fail with an anodal shock, no matter how good it is. Even if there's a 95% chance that you will succeed, right? So let's say, just to make it easy, there's a 90% chance you succeed, but you fail. So that means you shock 10 patients, one of them is going to fail with an anodal shock. You now reverse the polarity in that one patient. And let's say there's an 80 or 70% chance you succeed with cathodal shock. You deliver a cathodal shock and you say, oh, the cathodal shock worked, so reversing polarity is good. No, if you had delivered an anodal shock, there would have been a 90% chance on the second shock you would have succeeded. You just didn't do it that way. This is a phenomenon called regression to the mean in statistics. So this is much more than you wanted to hear, but basically, yes. My own personal view is, and I'm not, Sylvain knows me pretty well. I'm not categorical about a lot of things. There is no scientific justification for programming a cathodal shock.
Okay. And so if I understand well, so for a Boston or Biotronic, you will reverse to anodal shock, if I understand.
Correct.
And second, you are in the line